So hi everyone, I'm really pleased to be here. So this talk is basically split into two parts. If my thing will work. All right, so I've split it into two parts. So the first part of my talk is basically going to be things I've used Python for. So it's kind of a sales pitch for Python. So how many of you have been using Python for a year, less than a year? Less than a year, okay. Less than 5 years. All right, sorry. And greater than 1 year, of course, right? Yeah. Okay, greater than 5 years. All right. Okay, so it looks like I'm going to be preaching to the choir here, but it's all right. Maybe there are some things here that you have seen that are a bit unusual. But the goal is basically the first part I'm going to be doing a background. If this thing would work. All right, and do without. Okay, so the background is going to be about how I've used Python. The second part is going to be lessons that I've learned. And while the title says it's going to be for computational scientists and engineers, it's actually more general than that. The good thing is, I think Anand has covered a great deal about reuse, which is probably one of the most important takeaways that you can have from this talk as well. But I'm hoping that I have some other bits and pieces as well that kind of add to what he's done so nicely in his introductory keynote. So the overview is I've used Python for many years. And I've also used other languages. I've made many mistakes. I've learned from these mistakes, some of these mistakes, and hopefully I will communicate these back to you. So before I go on, started with BASIC way back. Then I actually encountered Lisp in AutoCAD, AutoLisp. I don't know if many of you know that AutoCAD actually has a Lisp engine built inside it. I was taught CS101. In CS101 we did Pascal. I think that was the same. Anand, I think you also had Pascal, right? CS101 was Pascal, right? I did terribly in that, by the way. And then learned C, 95, C++, 97, 98. And then I came across Python in 98. So I've been using Python ever since. So the first thing I got really my hands dirty with Python was there were colleagues in my class, in my lab. I was doing a PhD. I did my bachelor's in IIT Madras. I stayed on in IIT Madras to do a PhD. And my colleagues in my lab had three-dimensional data that kind of looked like this. Can we switch these lights off? May look a little better. So basically it looked something like this. These are iso surfaces, which means that at each of these surfaces the speed of the flow is constant, right? So basically they're interested in supersonic jets that are mixing. They had a lot of data and they wanted to visualize it. And they were not savvy enough to actually pick up a visualization library. So I had to write them scripts, and I chose to write it in Python. And I used this library called BTK to do this. And I generalized this later on, and then ended up building a little UI for it using a library called tk-enter. How many of you have used tk-enter or heard of it? Great, awesome. Okay, so I used tk-enter, slapped up a quick UI. I mean, I'm just a grad student poking around having fun. Put it out there on the internet, and people started using it, and it was my first open source contribution. And then I was like, wait a minute, Python seems so powerful. And a lot of the stuff that I was doing was routine. Build a button here, connect this button to that call, do all of this stuff. And I'm like, wait a minute, there has to be a silly, simple way to do it. This is very silly. I don't want to be repeating myself so many times. I don't want to keep doing the same mundane thing. This is one of the things that I find is very useful when you're programming. If you don't like to do grunt work, that's a great attitude to have when you're programming. The same problem was seen by people like Anand, right? People don't like to do grunt work and say, okay, I'm going to sit on abstract. It's much easier to just cut, paste, copy. But I don't like to do that. I like to make sure I don't want to type. I want to do minimum amount of typing. Even though it will take me less time to do that, it may take me 10 minutes to actually fix something by repeating myself. And I may take 1 hour to automate that process, but I prefer doing the 1 hour automation because I don't have to do it again and again. So what I did was I wrote a little tool which would parse the VTK module on the fly because Python had awesome introspection capabilities. And all of a sudden, given a simple Python script, I could pop up an automatically generated UI that looks like this with tkinter. And this was, I was still playing in C++ land. In C++, you can't really do some of these things. It's just too much pain to do these kind of things. So this was like awesome power for me. So runtime introspection, dynamic programming, and the power of automation and efficacy of brute force. That bug caught me early on. So I realized that this is really, really powerful. You're able to do a lot of stuff like this. So then in 2001 May, I generalized this whole thing and had a nice UI. It had a command line interface. I built this thing called MyAVI, put it out there on SourceForge when SourceForge was the fashionable thing to do at that time. It no longer is. And I ended up putting all of these bits and pieces that I had picked up and putting it all together and built a visualization system as a desktop application, shipped it, made standalone installers, the whole works in 2001, and it just took me about a month to do. Fortunately, I had very enlightened advisors who allowed me to do this kind of stuff. But then I also had my PhD work to do. So my PhD, I was looking at something that looks like this. So I was doing fluid mechanics. So this is a box, a square box, and I picked a square box because it's harder to simulate these kind of things. And you have a plus-shaped thing here that you see. That's like a mixie, and that's going round and round. And I want to simulate this problem. Doing this is actually not that straightforward. So we were building techniques called particle-based techniques. They're pretty well established in the literature. But we were implementing something that was efficient, that we could solve pretty nasty problems like this. So yeah, so you could run simulations like this. The arrows are basically vectors showing you the velocity, how things are moving. The red and blue is basically what's called vorticity, how things are spinning. It turns out it's very fundamental in fluid mechanics, so we're interested in looking at that. So all of this was written in C++, quite a lot of it. And I built it with scons. I started with makefiles, but then I converted that to using Python. Use Swig to wrap these to Python, so I can call all of this from Python. How many of you have heard of Swig? Swig, okay, not too many. So basically what Swig does is it allows you to call your C++ library from Python. Very straightforward to do, and I built many Python utilities on the side. This was all about in 2004. I then finished my PhD, but in the process I had to do a lot of analysis, and this is what all of you are probably familiar with, right? How many of you use NumPy, SciPy, Matplotlib? All right, great, fantastic. So how many of you use Graceplot? Wow, okay. I'm surprised there are actually 2-3 people who use Graceplot. Okay, so this is before Matplotlib. This is before Matplotlib became a big deal. Graceplot was the thing to use, and I was using it at that time. So then anyway, I finished PhD after all of these perambulations, doing all kinds of crazy things. Finished my PhD in 2004, and then I was looking for an academic position, and I had some time. So at this time I consulted for Untaught for about 9 months, half time. And I got to know about their open source stack called the Untaught tool suite, which is a really powerful set of tools, which fixed many of the warts that I had with MyAVI 1. So MyAVI 1 was not really a very scriptable application. It was more of a UI application. I did not have a clue about model view controller, model view presenter, and all of this stuff. So everything was all mixed in, a big masala mess. So I realized these were issues because people like Fernando Perez were saying, hey, I want to write a little script that does this, but I can't do it with your end. So we sort of rewrote the entire interface using the Untaught tool suite, and we made it something that you could do stuff like this. So here is an example where you have like 3 lines of code that spit out some data, one import, and then you can say mlab.surf, and it will actually pop up a little plot which you can interact with. And then you could write your own little dialogues. So you could create a visualization and have little dialogues. You can click on it, slide, drag. It's about 50 lines of code. But other people went on to extend it and use it, which was nice. And then we could do all really nice things with MyAVI, which I know I'm running short of time, but I'm going to do this anyways. So I'm going to maybe speed this up a little bit. All right, so what I'm doing is I'm launching MyAVI here, and what I'm going to show you is one of the cool features that MyAVI has, which is I'm going to click on that red button you see over here. And as soon as I click on this, I'll start doing UI actions. It will actually start recording stuff into a script. So let's watch it. I may fool around a little bit, trying to find my way. But essentially that window, so now I start opening a file. I load up a VRML file. and then say, all right, you can see that once I loaded that, it actually spat out some code. That code is injected into that, and it's actually executable Python. I'll do more stuff. I'll load up another file. So what this is doing is, it's basically showing us fire inside a room. There's some data which represents the room, and then this is showing me isosurfaces of temperature distribution in that room, right? And then I'm going to look at how the airflow is going through that room, all right? Something that you would expect some engineer who may want to do this, all right? And then I'm configuring things, setting various parameters on the UI and stuff like that, all right? Setting the view, making sure everything looks right, and then go back to the window there, and you see it's actually recorded a lot of Python stuff here, right? Close that, save it to a little script, close MyAVI, and now the nice thing is I can just say MyAVI2 minus x script, and it will load up that whole thing and reproduce that visualization exactly as I left it, all right? And all of that is executable Python code, right? And get better because I can actually edit this and make it a complete standalone script without even having MyAVI the application load up. I can just say Python script and it will pop it up. All right. So this was something that I could build as a non-CS kind of person with MyAVI. So the idea was Python basically allowed me the power to be able to build really complex stuff like this fairly easily. The entire effort that engineering that went into making this possible took me about a week to write, which is not a lot considering the kind of feature it is. So using all of this, I've been working on a research project called PySPH, where we look at simulating these kind of problems. So that's basically a dam of water splashing against some object, and then that object basically being displaced by that. Furthermore, you can do stuff like this, which is have elastic collision of kind of rigid bodies or deforming bodies and actually simulate some of these things. So this belongs to a class of techniques called SPH, smooth particle hydrodynamics. I'm not getting into the details, but essentially I'm working on things like this. So we basically built a framework called PySPH, where the thing we learned was, again, we don't want users to be writing high performance code at a low level. So the issue with some of these simulations is that simulation, that water hitting the SPH shape, takes about 40 minutes to run on this machine, using all the cores on this machine, which is a lot of time, and that's a small problem. If I increase the resolution, it will take like a day, 2 days, a week. So people need to write efficient code, but then they also need to have a high degree of dynamism in the sense that they want to change things, they want to modify things, and they may not really be HPC users. They may not really know the details of how do you actually extract the most amount of performance. So I found that many students, even at IIT, just were not able to do these kind of things. So we designed a library where you can write stuff in pure Python, very high level pure Python, and it automatically will generate high performance code. So for example, if you look at a typical example that we have, like here's a simple Python file that uses this library, it's about 88 lines of code. If you run it with just python cube.py, it will transpile this code, compile it, so that it will run on a single core very efficiently. If you just pass it a ---- openmp, it will compile it and make sure it can run on all cores. If you just say ---- opencl, it will use a GPU on your machine. If you instead say mpi run -np20 python cube, it will actually run it distributed across cluster. So the idea is, if you can build an abstraction at this level, users don't really care, right? They write their cube.py, and regardless of what they want, they can actually get it executed on the hardware that they have. So this again is done with Python, right? So basically you can compile on the fly, we can generate a bunch of stuff. A lot of this stuff uses techniques like what Anand was talking about, using the AST, parsing that, walking the tree, generating code. Now, once you can do things like this, if you have to publish research, you basically have to run a lot of simulations. And again, to automate this, you need tools to do this stuff. And again, I tend to use Python to do all of this. So I have a little framework which allows me to do distributed computation with this. All right, now that we know that Python is an awesome language, I also want to teach people how to use Python. So I ended up writing a web application which allows me to have students take tests, and it tests them automatically online using Django. And I'm going to skip this because I'm really running short of time, but you can also build things like web applications like this. This is called Vixen. It's basically an open source tool for field biologists to look at their media and be able to annotate them with metadata. And what you can do is stuff like this. So you have videos, you can attach arbitrary metadata fields like here, and as you see the video you can annotate it and save it, and then you can start searching over it and you can export it to CSV and stuff like that. A lot of people find it very useful. Turns out it's just about 5,000 lines of Python. It has a HTML based interface, it has a standalone installer, it's cross-platform, all this stuff you can do again with Python. So basically what do I use Python for? Pretty much everything, and I have a lot of fun doing it. So my sales pitch to you is, I think you've already been converted, so no point selling it to you, but there are diverse needs that you basically run through. So in 20 years of doing all kinds of stuff, you need to do a lot of stuff, and if you learn one language, Python, you can actually do a heck of a lot of stuff. It also has an amazing community, so that's great. And to spread this, there's a project called FOSSEE. I suggest you check it out. We kind of try to spread the adoption of open source in education. All right, so there goes my background. Let's get on with the lessons. So the first big lesson is Python's awesome. Right? You can do a lot of stuff with Python. So you should learn it and make sure you learn it well. The second lesson is more for, so how many of you are from computer science? Okay, please do us the favor, don't invent a new language. All right? Okay, and I know everybody is excited about DSLs, but again, don't create a DSL just for the sake of creating a DSL. Any fool can create a DSL. On the other hand, if you create a DSL in Python, right, there are ways to do it, you actually have a lot of power because you bring the entire baggage that the Python community has to offer, and you can use all of that stuff. So do everyone a favor, don't do these things, okay, in lighter vein. All right, so let's look at some basics. So some of this is probably going to be, for those of you who are advanced, is going to be like, oh, you know, I already knew this. Well, that's true, but if you're teaching other people and mentoring other people, maybe these tips will be useful for you as well. Right? So I've tried to cull those things that I feel are the most useful points. So the first thing is use a good editor, okay? Which means don't use Nano. Use some decent editor, and I am not going to decide what that editor is because I myself use Emacs, I switched to Vim and switched back to Emacs, now I use Spacemacs. It doesn't matter, pick an editor, okay? Master this editor, learn how to use it well. In particular, the features you want to look at are, you want command completion. This is not necessarily in sorted order of importance, but these are all important. You want the ability to be able to look up documentation or at least the doc string of that function. You absolutely want Pep8 support, okay? You also want reasonable linting support, and almost all editors worth their salt today will do this for you. You also find it useful to jump to source. So if I have a file and I want to be able to jump to the definition of that, you should be able to do that. An integration with IPython is a bonus. Not all editors have this, but if they do, it's really, really powerful, especially if you're doing stuff like data science. You want to just quickly execute, run something, it's really useful if you have that. All right, so apart from your editor, these are again command line tools that are really useful, that I have found useful. I'm sure you'll have your own set. Flake8, YAP, again if you have not used YAP, you may not use it. I don't use it personally because I like to format things myself, but YAP will auto format some of your code if it's not fitting a particular style guideline. The other less known tool, how many of you have used Grin ever? Have you ever heard of Grin? No one, all right. So have you ever found yourself sitting in a directory of a pile of source code and you say, you know, I want to know where this function is created. Where is it used? Usually your editor may help you with this, but very often you have to set up a project, you have to do this, you have to tag that entire stupid thing. There's a lot of work you have to do. But very often I am just diving around into a new library and I want to play around, say, hey, where's this defined, go and edit it and, you know, put a print statement or something. Use Grin. It's basically grep on steroids. It will avoid certain directories, but it will show me context. And very quickly I can find out, okay, go, and then I use less. How many of you use less? All right, okay, fine. So on the console, less and Grin are like my saviors. I can jump into any project, figure out what I want to look at, pick it out, look at it. And underlying all of this is don't hesitate to read code. You should be comfortable enough with a language, Python for example, that you should just be able to go, dig in, read the source, and be able to jump around and figure out what's going on with that. And of course goes without saying, learn Git and learn how to use it well. All right, this is again for very beginner programmers. How many of you are beginner programmers here? All right, great, good to know that. All right, so the big trick about programming is, first, know what every line does. You know, as in you should know exactly what, if you say x is equal to something, something, you should know what that something, something is. X is equal to linspace 0, 25, you need to know what linspace is, you need to know what x is, in the sense that what is its data type, how it behaves, all of that. So every line of code, if you know what it does, the instant you know that, you can read code. The second thing is, you need to be able to simulate how the dumb computer works, alright? And remember this, the computer is a dumb thing, it's not very smart. A lot of us have this opinion that, oh, computer is magic. No, it's not magic. It's actually an extremely dumb device, and the instant you realize this, you actually have a bit of less fear dealing with the computer. So as a beginner program, sometimes it's a little scary, right? Oh, if I do this, will this start frying up? No, it won't fry up. What's the worst you got to do? Reinstall your OS, big deal, it's just software, you can change it, alright? So the idea is, you shouldn't be scared of your computer. Just realize it's a dumb thing, you're giving it instructions. So imagine telling someone who's not very smart, telling them instructions that they blindly have to follow. The instant you think of it like this, programming actually becomes a lot easier. Okay, so now the first few steps, now that you're a little less scared of programming, the first thing you should ideally do is try to refactor your code into functions, little functions. Choose functions that do one thing well, make them small functions. So if a function goes over a page, it's too big. Try to refactor it into something that's less than a page. Another common beginner mistake, you'll see many beginners making this is, they'll have littered their code with input. Input, please enter 25, okay, please enter the number of values you want to run. This is absolutely useless, okay. The reason is, if I want to automate, I say, no, I don't want 25, I want 25 and 30 and 40. I'm not going to sit and type. And there are people who have actually written saying, please enter matrix, 10 by 10. Are you kidding me? You have to basically enter 100 entries manually on the console. It's completely useless, it's a rotten idea, don't do it. If you really have to do it, create a separate little function saying get input from user or something like that, where you can do whatever madness you want to do. But usually it's a lot more useful if you convert these into function which take arguments. Then you can automate the heck out of it. Do you understand? So inputs are not very useful, okay, generally. One other useful piece of advice before you start doing anything fancy, before you make a commit, review your own code. Just do a git diff, figure out what you've changed, review it, you will find bugs. I'm sure you'll find bugs. And get used to doing this, because you will eliminate a whole bunch of things that other people will start pointing out in your code. Okay, this is a good thing. Probably the most thing I want you to take away from this is something which again Anand mentioned, is programs must be written for people to read, okay, and only incidentally for machines to execute. This is a famous quotation by Abelson from SICP. Okay, so this is an extremely important thing. Most of us think we have it completely backwards. We think programs are meant for computers to run. No, they're actually meant for people. Computers can actually understand binary machine code, which you and I can't understand. So the point is, the code that you have is meant for other people, and usually it's you 1 year later. Okay, so make sure that you keep this in mind when you're writing your code, which follows us into this. Name things well. Code should be a pleasure to read. Comments should really be superfluous, and I'll come to this in a bit. Okay. So the first thing you can do, so look at this code. Okay, let's just take a minute to read it. These are actually rotten variable names, right? I'm saying A is Jan, Feb, whatever. I could have used months or something like that, right? D is, clearly I was thinking dictionary and I put D is some dictionary. And it's not obvious what I'm doing here. And here it's like, okay, I is input. Why on earth would I do something like this? Instead, if I wrote it like this, it's actually easier to read. You can say, okay, that's months. Month to mm is basically, you immediately get a sense of what I'm trying to do, right? I'm trying to convert, I have a dictionary which is a mapping which takes months and maps it to some mm. Mm is, again, you can use your intelligence of the domain to actually interpret what the user is trying to do, okay? And then it says month is get some input, and then print month to mm month. So it's much easier to read, so use better variable names. This is probably brain dead simple. Alright, now let's look at this code. Thank you. Really running short of time. Okay, all of these comments are absolutely useless, right? Because they're completely superfluous, and the problem with comments is you're never going to update them. Code, you're probably going to update. So remove these comments, they don't serve any major purpose. So here are two signs that you can look for. The first is, if you see a comment in your code, it's a dead sign that you can refactor. 2, you're cut pasting, refactor. These are two major signs that you should do refactoring. So let's look at a typical mathematical kind of sin C example. Initializing arrays x, y is some m grade phi is some sin x squared y squared, do some solving equations. So it's nice in some way, first time when you're programming, when you're a beginner programmer, you think those comments are nice because it gives you context. But actually, no. It would be much nicer had I done this. Because now it's a function, which means I can reuse it, which means I can call it however which way I want, which means I've parameterized it, which means it doesn't expose crazy new variables outside its scope. So there's a lot of advantage by just doing this, and it's a lot easier to read because now I know, oh, that's initialized. This is solved. And where you call it, where you use it is immediately more clear. Alright, so now the next step. So where do you use classes? Well, use a class if you have too much data to pass around. Classes should generally mirror your domain. So I'm going to skip this, you're going to probably have the slides anyway. Let's move on. So before you go on to the next step, start writing. Don't get overwhelmed because a lot of people are going to say, oh, there's this rule, don't do this, don't do that. Just start writing, okay? And don't let rules dictate these terms. Use these as a guideline, okay? And always remember this, coding is iterative. There is no perfect version of the code. At some point you're going to say enough is enough, I'm not going to do this anymore, alright? So move on. Alright, so let's see how we can do some more. Big mantra, don't repeat yourself. Thankfully he has covered everything there is to cover pretty much there, so I'm going to skip this part. I'm not going to repeat. The second major thing which he didn't talk about, I'm very happy he didn't, otherwise I won't have to talk at all, is invest in testing, and this really is a big deal. So it facilitates refactoring greatly. I had a story to tell, but maybe I'll try to tell you a concise story. So in my PhD, I had built a large C++ code base. And then I got a brainwave saying, this is not general, I want to completely change the implementation. I was shit scared making this change because, before my submission, I don't want to make any serious changes. But then I said, if I write test suite, so I wrote 140 tests in C++ unit, CPP unit or whatever, and then refactored the code and it was a breeze. Because I tested everything, I made the migration, all my tests passed, everything was great. So refactoring is phenomenally easy, testing makes it phenomenally easy to do refactoring. Facilitates faster development, there's another story, but I don't have time to tell you that story. And the third reason for testing is PyTest makes it so ridiculously easy to write tests that you have absolutely no excuse from writing tests. Because if you have used PyTest, it's just simple, write a function saying test blah blah blah, write your code, put in an assert, and you're done. So it's actually extremely easy to write tests. The other thing which I found really valuable is measuring your coverage. It's an easy thing to measure, you don't have to do a lot of data science, the library will do it automatically for you. It will tell you how much of your code is covered. The more coverage you have, the better your code is going to be. Invest in CI if you have the time to do it. This is one more testing tip that I'm going to share. Learned this from a friend. Basically you can give this simple markup which makes your tests a lot easier to read and understand. This is a BDD pattern. So here's an actual test in PySPH. Test assignment expression given that when code does this, then I expect this result. The reason this is nice is here the comments are at some level superfluous, but when someone is actually going to go and read this code, it makes a lot of sense. Because I can immediately say what the hell am I testing, what is input, and what is it, how am I testing it. It's obvious when you start reading this code. So this little bit of markup really makes your tests a lot more readable. Okay, the other major thing, how much time do I have? I have time, okay. Is to write intentional code, which is, let's read this code. It says check safety, if self.temp is greater than 650, blah, 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 blah. Warn user reactor critical, self.open escape valve, self.water flow plus equal to 10, some rubbish, right? It's not clear what my intent is. I just am checking some variables. On the other hand, if I wrote it like this, I said check safety, if self.reactor is critical, self.shutdown reactor. It's a lot easier to read, isn't it? Which means I don't need to interpret saying, oh, if temperature is greater than 650, it must be critical or any of that. I have essentially codified that logic. In this case, I've used a function. You would have also used a variable name. You could have said reactor is critical is equal to that. The point is, it makes it much easier for the person to read. Okay, there's another pattern that you can tend to use. The other useful thing is, sometimes when you create a class, you will have 40 methods. And clearly you don't need 40 methods to talk to this class, to this object. A whole lot of that functionality should have been actually segregated into private methods and some of them public methods. So the public methods are what your public API is. So it's a good idea for you to do this. For example, in the previous example, the reactor critical may not be something that I want to expose to somebody else. Check safety may be something I want to expose to somebody else. So if you rewrite it and just put an underscore, it's obvious to me saying, hey, this is not critical. This is the public API of the project. Again, this is something that allows people to read code much easier and make it a lot easier to follow what you're doing. Then comes optimization. Again, going to parallel what he said. First, get it working correctly, make it easy to read, and then you optimize it. Do not do optimization before the damn thing works. That's the worst thing you can do, all right? Because before it works, if you actually do it, you're not going to get the right result. You're optimizing it away, and God forbid you don't have tests, you're in deep trouble. So when you're doing this optimization business, try to make sure you write tests, because you may optimize away and you may get the wrong result. There's no point. So make sure you write it correctly, then make sure everybody can verify that it is correct by writing a test, then you sit and optimize it, all right? So you can do this a lot faster when you have test cases, because once you've written the test, you're done, all right? You can basically just optimize it and check everything works, great, move on. All right, but unfortunately for all scientists and engineers, performance does matter, right? So the first thing you need to learn as a beginner programmer is how to profile. There are a lot of tools that help you do this better. Not going to get into it because of lack of time. And one trick, having written a fair bit of this stuff, is try to use NumPy arrays, but be aware when you're trying to iterate over NumPy arrays manually in Python. There's this thing called unboxing, which will make your code 4 times slower if you did it with just a naive for loop, right? But there are tools to get around some of this. The other thing that I find particularly very, very useful is to try to break your computationally hard problem into manipulation of arrays, not necessarily vectorized. Even if you're going to do iterating loops over these, it's very easy to generate code, high performance code, really fast code, to work with arrays. And this will work on CPUs, it will work across CPUs, multi-core, it will also work on GPUs. So a good paradigm to fit most of your computationally hard algorithms is to try to make it things that manipulate chunks of arrays, okay? Like arrays, full blocks of arrays. I think this is one of my last few points, which is for a long running format, remember as a scientist, you will have data files. One thing I have realized is first 10 times I did it, I never versioned my data. So always have some way to version your data. Not necessarily, I don't mean Git version control. I mean actually being able to say that file was version of this. Then you can go back in time and pull this out. All right, and say you can have converters. You can start saying, oh, from version 1 go to version 2. This is an extremely useful thing because believe it or not, you may revisit a paper that you wrote 5 years ago and you may want to say, you know, what happened? And if the file formats change, you're finished. You can't go back. All right, you could go back with Git, but it's a lot of headache. Right? Eliminate that by, you know, having clean data. All right, I think I have what, 5 minutes left? 7 minutes left? 5 minutes left. All right, so I think I'm going to skip this because I am really running out of time. I'm going to have just 2 more slides. The first is, if you have a choice between automation and documentation, I would suggest you pick automation, because automation will not go out of date, especially if you have invested in CI. The tests will fail, if you're, but your documentation, nobody is going to tell you, oh, you missed this parameter, all right? So automate as much as you can. Finally, I think probably the most important thing, take pride in what you do. If you're putting it up out there, you'll probably do a better job. And that's a summary. Readability, consistency, and elegance matter. Write intentional code, DRY. Invest in testing and CI. Treat your examples and tests like your main code. Take pride in what you do. Thank you. Can I have do I have time for a few?